Hello, and thank you for attending this NIMH workshop on naturalistic stimuli and individual differences. I'm really looking forward to seeing everyone's talks and to seeing what kinds of questions are generated in the forum discussions and then to tackling those questions at the roundtable. I think it will be a very fruitful combination. In my lab, we use naturalistic stimuli for pretty much all of our research, but first and foremost, we study human memory. The kind of memory we study is episodic memory. And these are memories for specific episodes or events that are tied to the time and place in which the information was learned. And Doltolving described episodic memory as mental time travel. You send yourself back in time to re-experience that original moment. Another way to think of it is that it's the memory I use when someone asks me, "What did you do this morning?" I got up, I packed my kids' lunch, I drove her to school, I called a coffee shop, I ordered a coffee and a breakfast sandwich, and then I tried to drive to the coffee shop, but I got really lost. And while I was driving, I was listening to a podcast, and then it started raining. And my memory of those events is specific to those moments in time. It includes rich details about the locations and sensory attributes and objects and people that were there. Now, episodic memory is typically studied by showing people some simple stimuli like words or pictures or pairs of them, and later testing to see if they can remember them. An important feature of this kind of memory is that you learn it after one exposure. No reinforcement is needed. So like my morning, those events only happen one time and now they're in my memory. Now, I would like to suggest to you that much of the time when people use their episodic memory in real life, they remember past events and report them as a kind of narrative, just as I reported the story of my morning to you. And in fact, if you read about what literary scholars think that narrative is, one important feature is that the events only happen once and that they happen at a specific time or location, very much like Tolving's definition of episodic memory. In this talk, I'm going to show you what we see in human behavior and brain activity when people are engaging with realistic stimuli and remembering their experiences in a spontaneous manner. This is going to be a broad sample of many of the projects going on in my lab, not a deep dive. I started out with this work simply trying to understand episodic memory while making the input and output for the human brain more realistic, more like daily life experience. And over the years, as I've pursued that goal, the more I learn, the more important I think narratives are for understanding human memory and its underlying brain activity. So how do we study realistic experience in people who are trying to hold very still? We want to scan people's brains while they're having naturalistic experiences and remembering them. And that means that they won't be able to move. So we emulate real world experience using a movie. Movies have dynamic images and sounds. They depict real environments and social situations and emotions, and people love watching movies. While movies are different from real life in many ways, they have a lot of elements that we want for a naturalistic experimental stimulus. And as Gordon Bauer said, consuming stories has strong face validity as a task humans frequently perform with the goal of remembering. It's not the least bit artificial. It turns out that when different people watch the same movie, their brain responses become synchronized. And this is a very useful tool for studying the brain. I'm going to do a very brief explanation of this method, which is known as intersubject correlation. I'm guessing that it will appear in a lot of the other talks in this workshop as well, so hopefully a brief explanation will suffice. And if you want to know more, that Nastase paper is a great primer. So here is what I mean by synchronized. If you look at just one region of the brain, auditory cortex here, auditory cortex produces a complex response time course while the movie is playing, driven by the volume and by different sound textures in the movie audio. That complex response time course is the same across different people because everyone is hearing the same sound stream. If people are just lying in the scanner listening to nothing, you don't see synchrony across people in auditory cortex. Each part of the brain has its own response time course depending on what features of the movie stimulus it cares about. And if you calculate this correlation for every part of the brain, you can make a map of the synchrony across people. So in this kind of analysis, one person's brain activity is the model for another person's brain activity. You don't know exactly what in the stimulus is driving the brain response, but you know how reliable the response is. Something in the stimulus evoked brain activity in this region, not necessarily a pulsive activity, but a consistent response. So this is how you examine what kinds of stimuli drive responses in any given brain region. And in these kinds of experiments, we find that a non-visual stimulus does not drive visual cortex reliably. A non-auditory stimulus does not drive auditory cortex reliably. And a non-narrative stimulus does not drive certain areas reliably. Those are interesting areas, often overlapping with the default mode network. And there are many studies that investigate this. If you're looking for a starting point in this literature, I think Lerner 2011 is a good choice. So now let's turn to the question of what happens when narratives are input to the brain and narratives are output from the brain. Psychologists have been on this tip for a very long time, so it's exciting to be able to connect this beautiful older literature with new neuroimaging methods and natural language processing techniques from machine learning. Let me show you this very simple diagram as a way to orient ourselves. Memory experiments typically have an encoding phase and a retrieval phase. Encoding is when you're presented with the stimuli, and retrieval is when you're tested for what you remember. Now, both encoding and retrieval can vary in terms of how narrative-like the experience is. So in this corner, we have non-narrative encoding material and a non-narrative retrieval test. For example, the encoding stimuli are random words, and at test, you see one word at a time and answer old, new, whether you've seen it before or not. And in this corner, we have narrative encoding material and a narrative retrieval test. For example, the encoding stimulus is a Hollywood movie, and the test consists of asking the subject to retell the movie plot in their own words. In this corner, we have narrative encoding material and non-narrative retrieval test. So the encoding stimulus is still a Hollywood movie, but the test is maybe a true-false questions about the movie. All three of these approaches are found in the memory literature, and they each have their strengths and weaknesses. In this talk, I'll mostly show you studies that fall into the two right-hand quadrants of the diagram. The top left corner is the most mysterious. Here we have a non-narrative encoding stimulus, a list of random words, for example, and then the subject turns it into a narrative at the time of retrieval. In our review, we didn't find any study exactly like this, but we suggested that autobiographical memory might have this quality. And I will return to this idea at the very end of the talk. A key idea in memory is that when you remember a prior experience, this involves regenerating neural activity patterns from the time when you had that original experience. Each person has their own brain pattern at encoding and at retrieval. For fMRI data, we calculate this as a correlation of multivoxel patterns in a given brain area between encoding and retrieval. This is the degree of reactivation. And remember what I told you about synchrony of time courses across people. It turns out you can also do this with the local spatial patterns in each brain region. It can be informative to calculate correlations between subjects during encoding. This tells you the reliability of signals that were driven by the input stimulus for a given brain area. And similarly, calculating correlations between subjects during recall tells you the reliability of signals that were driven by remembering. For movie data, we typically do this at the scene level. We split the movie into scenes according to major changes in the action, and then we look in one brain region at a time, calculating correlations between encoding and recall, or between subjects during encoding or between subjects during recall. The correlation between random scene pairs serves as the baseline. So this is essentially a test of scene discriminability. We often have people recall a movie out loud in the scanner. They choose their own words and retell the story as best they can remember it. The length of recall will, of course, vary a lot, but as a ballpark for this 15-minute movie, we got recalls ranging from around 10 to 45 minutes. Very detailed. During recall of movies, we see a consistent pattern of brain regions where there is strong intersubject correlation, largely in the default mode network and higher level visual areas. And here's that set of regions on the right replicated in a second data set with different movies, different subjects, and a different scanner. In these maps, we're merely using the recall as a way to identify when people are remembering each scene in the movies. But doing this glosses over all of the rich detail that's present in people's spoken recollections. So in a project led by my postdoc, Lisa Mez, We ask whether the nature of what people say can be linked to the neural reactivation properties of each scene. Lisa developed a rubric to assess for every sentence of recall whether the subject's description was a temporally precise recounting of the movie events or whether it was a summary across a longer time period. That is, some sentences temporally compress the movie to a greater degree. And Lisa found that when temporal compression is greater, neural changes between movie and recall activity patterns are also greater. And importantly, these are neural changes that are common across subjects, not merely noisier reactivation. Another way that our lab tries to understand how narratives drive memory is by quantifying the relationships between the events from which the entire movie is composed. In this study led by Hongmei Li, we turn each movie into a network of events where the edges between nodes are based on the semantic similarity or the cause-effect relationships between events. The network properties then predict recall behavior and brain activity. And our specific hypothesis for this study was that events that are more interconnected with each other will be the ones that are the best remembered. And this is based on prior work in the narrative psychology literature. We also predicted that the property of interconnection would drive default network activity. Semantic relationships between events were calculated using sentence embedding similarity, in this case, Google's universal sentence encoder, and causal relationships were derived from human judgments. The property of interconnectedness is simply the degree centrality of the event node in its story network. And Hongmei found that semantic event centrality predicts recall performance, as well as intersubject correlation in posterior medial cortex during recall, and event offset hippocampal responses during encoding. The behavioral effects were strong for both semantic and causal centrality, and the neural effects in PMC were stronger for semantic centrality than for causal centrality. I think there's something important that we still don't understand about the role of causal relationships here, so this is going to be a line of future questions. We replicated the behavioral effects in a pre-registered study with 10 new movies. And all of these behavioral and brain data will be public once the manuscript is out. Now, we often say that movies and narratives are dynamic, which means that their many features are changing in a complex manner across time. Well, when you engage with the narrative, your experience is dynamic too. It's not just a passive input channel. You're actively shifting your attention and anticipating the future, which is one of the reasons that movies and stories are so engaging. In this study led by Boudica Bulana and Anna Hu, we asked what predictions people make as they engage with an ongoing movie. While participants watch a movie, we stop them every few minutes and ask them to type out what they think is going to happen next. And we jitter these stops and collect predictions from many subjects so that for every 10 seconds of the movie, we can calculate the similarity across different people's predictions, again, using sentence embeddings. So this allows us to create a time course of consensus. That is, for some moments of the movie, people tend to predict the same thing, and at other times there are more diverging opinions. Our hypothesis was that intersubject similarity in brain activity would be related to this prediction consensus score. This is a work in progress. The short story is that prediction consensus predicts neural intersubject correlation in some movies, but not others, and we don't yet understand why. And so our next step is to try and improve the accuracy of the sentence embedding measures by collecting direct human judgments of similarity across predictions. This interface allows people to read the predictions for a given stop in the movie and create categories which they name. This technique is used in image similarity experiments, and here we've worked with the Meadows research team to adapt it for text. Our hope is that with these direct human judgments, we can more confidently say that prediction consensus is related to neural intersubject similarity in certain movies and not others, and start to examine the reasons why. One of the great promises of naturalistic stimuli is that by using them, we'll observe something about the brain that we couldn't see using more limited stimuli. So I think it's critical to characterize the signal properties of brain activity during natural stimulation and to expect the unexpected. In this project led by Yunjung Li, we push back on the idea that there's a unique brain pattern for each movie scene. The typical approach when analyzing movie data, as I described at the start of this talk, is to collapse each scene into a single voxel activity pattern and then test the discriminability of the patterns. In pretty much any movie data set, you will get above chance level with this test, meaning that you can identify scenes across subjects based on the neural pattern. That can be seen here as the warm diagonal in the matrix. But another thing that's quite clear here is that there are a lot of high correlations off of the diagonal. And I don't think anybody thinks that that's all noise. But what it is has not been well examined yet. When you expand this matrix from scenes to individual TRs, you can get a closer look at the similarity structure. And now you can see that scenes are composed of multiple clusters or component states that repeat across multiple scenes of the movie. Yunjung used k-means to cluster the TR level patterns in movie data into groups. And here you can see that around 9 clusters looks like it might be enough to do a good job of organizing patterns in posterior medial cortex. We decided that we would choose the value of k based on the standard method for measuring memory reactivation. So in this data set, people watch a movie and then recall it out loud. We do the standard reinstatement analysis, but replace each TR pattern with the mean of its cluster. And here, Yunjung finds that 9 clusters are sufficient to achieve 95% of the reinstatement strength you get if you use the original data. So despite all the seeming complexity of the stimulus and the brain response, there is a simpler structure here where in this brain region, at least, 9 or 10 component patterns explains almost everything. Yunjung's doing follow-up work here, trying to understand the nature of those 9 or 10 component patterns and finding some evidence that they're linked to distinct groups of actions in the movies. Another unexpected property of the naturalistic movie brain response was something we saw when we put a few shorter movies into one scan instead of having one long one. It turns out that there are very large transient responses at boundaries between movies. And these transients actually have a voxel pattern which is consistent across different movies. Even more interesting, that voxel pattern is consistent between movie and recall. In the spirit of the individual differences part of this workshop, Hongmi made these beautiful figures showing that this transient response looks, showing what the transient response looks like in each individual subject. And I think it really nicely visualizes that there's a strong coarse spatial similarity across subjects and additional fine scale structure that's specific to each person. Everything I've showed you up to now is about what we see in the brain when we use movies and stories as stimuli. And in the last part of this talk, I'm going to show you a few studies where we try to use what we learned from working with movies to go in new directions. So what is missing from a narrative? What I mean is movies and narratives are pretty naturalistic compared to a random list of words, but they're still different from real life in some important ways. One critical way that movies aren't like real life is that they're made for one-way consumption. Of course, it's not a totally passive zombie experience like this cartoon is poking fun at, although it's probably kind of familiar to you. As I said earlier, you're often making predictions and actively engaging in other ways with a movie or story. But nothing you do will change what happens on the screen. That is a fixed input stream. It's obvious, right? In real life, you have control over what you look at, where you go, and who you talk to. You choose which input streams to attend to moment by moment. So in this experiment, we try to take one step in that direction by giving people choices which control a narrative. If you ever read those choose your own adventure books where you get to flip to page 24 if you want to confront the dragon and flip to page 90 to run away, you already know what I'm talking about here. And this project is really complicated. So we have a big team of people all contributing different essential pieces. Sian Lee, Boudica Balana, Anahu, Savannah Bourne, and Ria Giuliano all contribute to this project. In this experiment, people read a story, one short event at a time, one sentence at a time. And the first story we used is one we found on the web and modified slightly, which takes around 5 minutes to read. It's a sort of prequel to Alice in Wonderland. Every several events, participants get to make a choice about what they want to do next. And when they reach the end of the story, they produce a free written recall of whatever they can remember. There are 3 conditions. In the free route condition, participants make choices and always get what they choose. In the yoked condition, participants make choices, but they don't always get what they choose. Their root is actually yoked to a prior free root participant. And in the passive condition, participants don't see any choices, they just read the story. Their root is also yoked to a prior free root participant. First off, we didn't find any difference in overall recall between free and yoked, so they're equated there. We haven't run the passive condition yet, but we expect performance to be a bit lower on that. Next, we looked more closely at yoked subjects. At any given decision point, these subjects could have their choice granted or not granted. We think of this in terms of prediction. Making a choice is essentially like making a prediction. If they get what they choose, their prediction is confirmed, and if their choice is not granted, their prediction is violated. Based on past memory literature, you would expect here that memory should be better for choices and events when predictions are violated. But actually, we saw the opposite. Memory was better for events where predictions were confirmed. This was surprising, and we're thinking now about how emotional investment in the choice or storyline that you wanted could be driving memory for these events. The flip side of looking at how people make predictions is looking at how the recent past influences the current moment. There's a lot of work on this using stories and movies, and here I'm talking about the studies on temporal receptive windows. But what about when people choose their own recent trajectory? In this experiment, we have subjects look at a complex scene, it's a static image, and talk about what they see, walking through the picture step by step in whatever order they wish. We segment the images and turn their spoken description into a trajectory through the scene. Now you can ask, what path do people take through the scene? And if two people have a similar path, does that predict their neural similarity to each other at any given segment? And in early results, we see that prediction holding true in posterior medial cortex. This technique is called intersubject RSA. It's a powerful way to do individual differences analyses with naturalistic stimuli, and I'm sure you will see others in this workshop talking about it as well. Now, the last study I'll talk about today, remember I told you that I would come back to the mysterious top left corner of this chart. This is a non-narrative encoding stimulus, like a list of random words, and then the subject turns it into a narrative at the time of retrieval. It sounds like a weird experiment, but maybe this is actually similar to autobiographical memory. When you walk around in the world, your experience is a series of events, but those events might not have any strict logical connection to each other. They probably don't form an obvious story arc, at least until later when you remember them. It's when you remember and describe your past experiences that they become more story-like. Well, in this study, we try to capture that process by having people do everyday activities. Of course, there is already a huge body of work on autobiographical memory, but one thing that's really hard to get in such studies is brain data during encoding, because we can't yet scan people during daily life. In this study, we're trying to get around that by having people use the internet. We give them 16 different common internet browser tasks that they can choose from, like reading Wikipedia or shopping or finding a place on Google Maps. And then we screen record them as they do whichever tasks they want on the real internet. And I think this experiment pretty closely resembles daily life experience for a lot of people, maybe especially during the pandemic. After around 45 minutes of this, we have them retell what they remember. And they write a lot. It's a similar length of recall to what we get for the same length of movie. Here are recall trajectories for 5 different subjects. You can see they vary a lot. We've already started scanning people watching video and recalling these activities. And the next step will be to have people actually do these internet activities inside the scanner. One thing that will be really interesting to look at in these data is whether some of the principles of recall that we see in narratives still hold true for memories like this. One difference that's already clear is that they remember things very non-chronologically relative to recall of a movie narrative. And I'd like to come up with an objective method for scoring the degree to which people narrativize during recall, and then look at whether that tendency varies a lot across people and whether it's predictable from brain activity during encoding. So in conclusion, I hope I've given you an informative, or at least entertaining tour of some of the ways we use naturalistic stimuli and behaviors to study memory. Thanks to everyone in my lab and collaborators, and thank you for listening.